Hello everyone. Today we are going to derive the finite element formulation for one-dimensional potential flow. So I assume that you have already developed a little bit of friendship with Galerkin's weighted residual method, particularly the weak form of Galerkin's weighted residual method, in order for you to completely understand the derivation that we are going to do today. So first I will derive the continuity equation. Once we have the continuity equation, so that is going to be the governing differential equation. So you know where the story will go. If you have the governing differential equation, then you can extend the governing differential equation to its weak form. Then you have the finite element equation. You will be having a stiffness matrix, not stiffness matrix to be very precise. You will be having a matrix that is analogous to stiffness matrix, and a matrix that is analogous to displacement matrix, and a matrix that is analogous to force matrix. So the structure is going to be just the same. So first, let me establish the physical scenario. Just imagine there is a fluid flow. So I'm just going to represent the fluid. I'm not just going to tell you the direction. The fluid need not necessarily flow from the left towards the right. Maybe the fluid is also going towards the screen. So it's a two-dimensional representation of a three-dimensional situation. So fluid can also go from the bottom towards the top, okay? So for now, I'm just going to localize my attention only on a small calculus element, so that you could see. So that is the small calculus element that I'm just going to fix my attention only on the small calculus element. So let me represent the hidden lines in this small calculus element. Okay, so the length of this calculus element is going to be dx, and the depth is going to be dz, and the height of this calculus element is going to be dy. Now let us consider the fluid that is going from the left side towards the right side. Of course, fluid also flows from the other two directions. Let us say that the fluid is also going to flow from the bottom towards the top, but for now, let me consider the fluid that is going from the left towards the right, which means that the fluid is going to enter this phase. So I'm just going to represent this phase by shading it in red color there. So the fluid is going to flow from the left towards the right. Okay, the fluid is flowing in this phase, through this phase. Okay, and it is going to come out of this phase. So we can call this as the red phase. So it comes in through this red phase, and it is going out through the red phase. So let me represent the fluid that is coming in and the fluid that is going out. So the mass flow rate, you have the formula for mass flow rate, which is very easy. So it is simply, by convention, it is rho AV. Okay, so where rho is the density, A is the area. In our context, the area is the shaded red area. V is the velocity through which at which the fluid comes. Okay, so that is going to give the mass flow rate through a particular area. So let us do this. So what is the mass flow rate of the fluid that is coming in, and what is going to be the mass flow rate of the fluid that is going out? So I'm just going to write the equation for that. So here we go. The mass flow rate of the fluid that is coming in. So fluid M, mass flow rate of the fluid that is coming in, is given by this equation rho AV, but rho is density. But what is this area? It is the shaded red area. So what is the shaded red area? Height into depth. It's going to be dy into dz. That is the shaded red area. Rho AV, V is for velocity. What is the velocity of the fluid that is coming in and it is going out? It is coming in along the left side. So the fluid velocity that is coming, its velocity is denoted by the notation u, and the fluid that is coming along the vertical direction. So that velocity is going to be denoted by the notation v, and the fluid that is going in this direction, that velocity is going to be denoted by the notation w. Okay, so u for the fluid that is coming from the left side towards the right side, so it's flowing along the x direction. So it's rho a v. So v for the velocity, so it's the velocity of the fluid that is coming in. Okay. Now that's the quantity of fluid, mass flow rate, quantity of fluid that is coming in. So now what is the mass flow rate, the quantity of fluid that is going out? So that is given by this equation m out. So it is the same equation. It is rho a v. So let me represent that. It is the rho area is dy dz and the velocity is u, but let us say that there is a small change. Okay, how that change comes, let us think about that a little later. For now, just accept my word for it. Let us say that there is a small change. Now, how do you represent that change? So I'm saying, let us say that it is gaining some fluid. Okay, so the gain in fluid is represented by, so the small change del. Okay, some small change to the existing quantity of fluid that is flowing per second. It is del rho density into dy dz into u. Okay, that is a small change. Okay, and you could see that the fluid is gaining some mass. How it gains, we will see that a little later, but assume that the fluid is gaining some mass. If that is the case, it is gaining some mass along the x direction. So what I will do is I will just multiply and divide by del x. So I'm not going to do any damage to this equation. Mathematicians will not allow us to do this way, but simply I'm multiplying and dividing by del x. In the next step, I'm going to write this equation as rho into dy into dz into u plus, for a very small change, I can conveniently write this equation as dou of rho dy dz into u divided by dou x into dx. I'm putting partial differential equation because, of course, the velocity is going to be a function of x, y, and z. So this is the expression for the quantity of fluid that is going out. Okay. Now, how much fluid, what is the gain in the fluid? So that can be represented as the difference, right? So what is the difference between the rate of fluid, quantity of fluid that is going out per second, minus the quantity of fluid that is coming in per second? So that should represent the gain. Okay, so let me write that equation. So it's going to be rho into dy into dz into u plus dou of rho into dy into dz into u divided by dou x into dx. Okay, that is the quantity of fluid that is coming out minus the quantity of fluid that is coming in, that is given by this equation rho into dy into dz into u. Okay, so that is the quantity of fluid that is coming in along the coming out along the x direction minus coming in along the x direction. Okay, in exactly the same fashion. Okay, in exactly the same fashion, I can also write the quantity of fluid that is coming out along the y direction and coming in along the y direction. I can represent that. So the way I do that is the gain is given by, so let us say that the quantity of fluid that is coming out along the y direction is going to be greater than the quantity of fluid that is coming in along the y direction. That is going to be the gain, plus I'm going to say it's going to be rho into, instead of dy dz, it will be the dx dy, right? It is coming in along the y direction, so it's going to be dx dz. So it is going to be this area. So I will shade that area for clarity. So we are going to talk about this area and this area. Okay, so the shaded yellow area. So if that is the case, then it's going to be rho into dx dz. So that is the shaded yellow area, dx dz. And the velocity with which the fluid is coming in, it is v, okay, plus dou by, of course, the change is happening along the y direction, dou by dou y into rho into dx into dz into v, whole divided by, multiplying and dividing by dy. Yeah, that is it. Okay, so minus the quantity of fluid that is coming in, which is given by this expression, minus rho into dx into dz into v. So that represents the quantity of fluid that is coming in along the y direction. In exactly the same fashion, I'm just going to represent the quantity of fluid that is coming in along the z direction. So let me change the color. Maybe I can use the green here. I'm talking about this area. Okay, so this shaded area, the green area, which is going to be dx dy. Okay, and the velocity with which the fluid is coming in is going to be represented by the notation w. So the quantity of fluid that is coming in minus the quantity of fluid that is going out, plus it is going to be rho into, the area is dy dx dy, dx dy into w, plus dou by dou z of rho into dx dy into w into dz, minus rho into dx dy into w is going to represent the quantity of fluid that is coming in along the z direction, and these terms represent the quantity of fluid that is going out along the z direction, and this will represent the gain. Okay. Now we can simplify this equation further. What we can do is we can cancel the terms, these two terms. I think we can cancel these two terms. We can cancel these two terms. We can also cancel these two terms. I can now write the simplified equation here. I can pull all the constants outside of this equation. So if I just pull all the constants outside of this equation, I will be getting density is a constant that I can take it outside the equation, rho into dou u by dou x into dx dy dz. So I'm just representing this particular equation in this form. Plus, I can pull the density outside. It's going to be rho into dou v by dou y into dx dy dz, taking all the constants outside and keeping only the field variable, which is the velocity, plus a rho into dou w by dou z into dx dy dz is equal to the gain. Okay, so this is going to represent the gain. Now what we will do is we will divide this by dx dy dz on the left side and the right side. But before I do that, suppose if this value is negative, what does it mean? How can that value be negative? It can be negative if the quantity of fluid that is coming out is going to be less than the quantity of fluid that is coming in. In that case, it represents the loss. When do you think there will be a gain? So inside the small calculus element, there is going to be a gain inside the small calculus element. Suppose the gain indicates that if there is, this is the small calculus element that we considered. Gain means there is some kind of source that is actually pumping the fluid inside. Okay, some kind of source that is pumping the fluid inside. Okay, so that is what means a gain. Okay, a loss in the sense there is some kind of fluid that is being pumped out, which means there is lost, right? So I'm going to represent that loss in the sense there is some kind of fluid. So there is a sink that is going out. So that represents the sink, which means there is a loss. And if there is a gain, it means that represents the source. For an incompressible fluid, when there is neither a sink or nor a source, Let us assume that there is no sink, there is no source, and also we will assume that it is incompressible. In that case, there is neither gain nor loss. So in that case, it will be zero. Whatever quantity of fluid that is coming out should be equal to the quantity of fluid that is coming in. In that case, this right hand side will be zero. So we will consider the scenario of incompressible fluid. In that case, this particular equation will still be rho into dou u by dou x into dx dy dz plus rho into dou v by dou y into dx dy dz plus rho into dou w by dou z into dx dy dz should be equal to 0 because there is neither source nor sink, and it is also a compressible flow. I'm sorry, incompressible, right? Underscore the word incompressible. If I had used the word compressible, my apologies sincerely. So now I can cancel the left-hand side and the right-hand side. What I mean by cancel, I can multiply and divide by 1 by dx dy dz. So what happens is these terms go away. I can pull them outside and throw it to the right side. So those terms vanishes. So I can also do exactly the same for density. I can throw this outside to the right-hand side. So density also disappears. So I'll be getting dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So this is going to be your continuity equation. So for incompressible flow, okay. Now, let us consider the flow along the x direction. If the flow along the x direction, let us say that the flow along the x direction, we will consider. Let us say that what is driving this flow, okay. Let us see. Suppose somehow you have a pressure on this side. I'm going to represent the pressure by the notation phi. Let us say that the pressure along this side is, say, 10 meters. And the pressure on the right side, let us say that it is only 2 meters. Okay. So the pressure is denoted by the symbol phi, and the pressure on the left side is 10 meters, and the pressure on the right side is 2 meters. Now we can say that whatever factor is that is driving this fluid flow should be the pressure, because the fluid, now let us say that it is actually flowing along the x direction because of the difference in pressure, because of the difference in potential. That is what is driving the fluid flow. So now that allows me to write the equation dou phi by dou x. So assuming that this is separated by a small distance del x, and for a very small distance, then dou phi by dou x should be proportional to the velocity u. Okay, so that's how this equation comes, because the velocity is a manifestation of the difference in pressure. Okay, the difference in pressure is what is actually producing the fluid flow. Okay, so in order for me to eliminate this proportionality, I have to introduce a constant. So let me introduce the constant. Dou phi by dou x is equal to k into u. Suppose if this fluid is flowing through a permeable membrane, some kind of membrane throughout this fluid flow, then this K will be permeability, right? So that is actually going to be decreasing the fluid flow velocity. So the permeability value can vary from 0 to 1, because if there is no membrane, and if the pipe is perfectly smooth, we can assume that K value to be 1. Okay, so if we assume K value to be 1, then what happens to this equation? Dou phi by dou x will be equal to u. Okay, we can also consider the same scenario, but this time the flow along the y direction, in which case it will be dou phi by dou y will be equal to v. And we can consider the flow along the z direction, in which case it will be dou phi by dou z is equal to w. So now I have three equations for u, v, w. What I can do is I can take this value of u and I can plug it here. I can take this value of v and I can plug it here. Let me take the value of w and I can plug it here. So what happens to this equation? Let us try this. If I just plug the values of UVW, this equation becomes dou by dou x, and the value of U is dou phi by dou x, plus dou by dou y, and the value of V is dou phi by dou y, plus dou by dou z into the value of W is dou phi by dou z is equal to 0. So this equation can further be simplified into dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. Okay. So this is our famous Laplace equation, but for two-dimensional problem, there is no flow along the z direction, in which case this equation reduces to dou squared phi by dou x square plus dou squared phi by dou y square is equal to 0. And for a one-dimensional problem, it will be dou squared phi by dou x square is equal to 0. Okay, this is for one-dimensional fluid flow. So this is going to be our governing differential equation. But when we do the finite element formulation, in the next part, we are going to derive the finite element formulation for 1D dimensional fluid flow. So I'm going to modify this 1D equation slightly a little bit. I'm just going to add some details to this equation because we have set some of the terms to be, we have ignored certain terms. For example, we have, when we multiplied and divided by the volume on the left side, so you took this dx, dy, dz on the right side, so this volume just vanishes, right? So we are not going to do that for 1D. We need it for finite element formulation. So we will keep the volume, okay? And also what we will do is, we may assume that the permeability K is equal to 1. So we are not going to assume K is equal to 1. We will keep it so that we can come up with a very generalized equation, and it's going to be extremely useful. So we will see that in part 2 of this video. So thank you all for your patience.